Article 700.12.5 of the National Electrical Code, or NEC, addresses generators in emergency systems. It specifically concerns the use of generators as a power source for life safety lighting and other critical systems. The core requirement is that generators cannot be the sole source of power for emergency systems unless they are equipped with an auxiliary power supply. This regulation is in place to prevent any interruption of power to life safety circuits during a power outage, which could pose a significant safety hazard. The NEC mandates that emergency systems, especially those related to life safety, must have an immediate and reliable source of power upon failure of the normal power supply. Generators, while commonly used, have a startup time. If a generator takes longer than 10 seconds to become fully operational, an interim power source is required to bridge the gap and maintain continuous power to essential systems. This auxiliary power supply ensures that life safety lighting, exit signs, fire alarm systems, and other critical equipment remain functional without any break-in service. Acceptable auxiliary power supplies include battery packs, uninterruptible power supplies, or UPSs, or other equivalent systems capable of providing immediate power. These systems are designed to automatically engage when the normal power supply fails, providing power to emergency circuits until the generator starts up and takes over. The auxiliary power supply must have sufficient capacity to power the connected emergency loads for the duration specified by applicable codes and standards. This duration is typically determined by local building codes or the authority having jurisdiction. It is crucial to select an auxiliary power supply that meets these requirements to ensure compliance and, more importantly, the safety of building occupants. The NEC guidelines are very precise when it comes to the startup time of generators. While some generators can start within a few seconds, others, particularly larger units or those with complex control systems, may take longer. The code recognizes this and mandates that if the generator's startup time exceeds the acceptable threshold, an auxiliary power supply must be in place. This requirement is non-negotiable for life safety systems. The auxiliary power supply should be regularly tested and maintained to ensure its reliability. Battery-based systems, for instance, require periodic testing of battery capacity and replacement of batteries as needed. UPS systems should be checked for proper operation of their internal components and battery health. Regular maintenance is essential to guarantee that the auxiliary power supply will perform as expected during an emergency. It is important to understand that the purpose of emergency lighting is to provide sufficient illumination to allow occupants to safely evacuate a building during a power outage or other emergency. These systems are not intended to provide normal lighting levels, but rather to offer enough light to guide people to exits and prevent panic or accidents. Life safety lighting circuits are specifically designed to be independent of normal lighting circuits and are powered by the emergency power system. This ensures that even if the normal lighting fails, the life safety lighting will remain operational. When designing an emergency power system, it is crucial to carefully calculate the load requirements of all connected emergency circuits. This includes lighting, fire alarm systems, communication systems, and any other equipment deemed essential for life safety. The auxiliary power supply must be sized to handle the total load and provide power for the required duration. Overloading the auxiliary power supply can lead to premature failure or insufficient power, compromising the safety of the system. In addition to the NEC, other codes and standards may also apply to emergency power systems. Local building codes often have specific requirements for emergency lighting and power, including the minimum illumination levels, duration of power supply, and testing procedures. The authority having jurisdiction, or UJ, typically enforces these codes and standards and has the final say on the acceptability of an emergency power system design. Compliance with these codes and standards is essential to ensure the safety of building occupants and to avoid potential legal liabilities. When discussing emergency power systems with clients or other stakeholders, it is important to clearly communicate the requirements of the NEC and other applicable codes. Explain the importance of having an auxiliary power supply for generators with longer startup times and emphasize the potential consequences of not complying with these regulations. Provide supporting documentation, such as copies of the relevant code sections, to back up your recommendations. It is also helpful to provide examples of how emergency power systems have saved lives in real-world scenarios. Highlighting the potential risks of not having a reliable emergency power system can help convince stakeholders of the importance of investing in this critical safety feature. Consider a situation where a fire breaks out in a building and the normal power supply is interrupted. If the emergency lighting system relies solely on a generator that takes 30 seconds to start, there will be a period of darkness where occupants are trying to evacuate. This can lead to panic, confusion, and accidents, potentially resulting in injuries or even fatalities. However, if the emergency lighting system is equipped with a battery backup or UPS, the lights will come on immediately, providing occupants with the illumination they need to safely exit the building. This simple example illustrates the critical role that auxiliary power supplies play in ensuring life safety during emergencies. Emergency power systems are not just about complying with codes and regulations. They are about protecting lives and preventing injuries. It is important to approach these systems with a focus on safety and reliability, ensuring that they will perform as expected when they are needed most. When selecting components for an emergency power system, it is crucial to choose high-quality, reliable products from reputable manufacturers. Avoid cutting corners on cost, as this can compromise the performance and longevity of the system. Consider factors such as the product's warranty, certifications, and track record of performance. It is also important to ensure that the components are compatible with each other and that they meet the specific requirements of the application. The installation of an emergency power system should be performed by qualified electricians who are experienced in this type of work. Proper installation is essential to ensure that the system functions correctly and that it meets all applicable codes and standards. The installation should be carefully inspected and tested to verify that all components are properly connected and that the system is operating as designed. After the emergency power system is installed, it is important to develop a regular maintenance and testing program. This program should include periodic inspections of all components, testing of battery capacity, and functional testing of the entire system. The results of these tests should be documented, and any deficiencies should be promptly corrected. Regular maintenance and testing are essential to ensure that the emergency power system remains reliable and ready to perform when needed. The NEC provides specific requirements for the testing of emergency systems. These requirements vary depending on the type of system and the occupancy of the building. In general, emergency systems should be tested at least monthly and annually to verify their proper operation. The monthly test typically involves a brief interruption of the normal power supply to verify that the emergency power system starts up and provides power to the connected loads. The annual test is more comprehensive and involves a longer duration test of the system's ability to sustain the emergency load. The NEC also requires that emergency systems be inspected periodically to verify that they are in good condition and that all components are functioning properly. The inspection should include a visual examination of the wiring, connections, and equipment to identify any signs of damage or deterioration. Any deficiencies found during the inspection should be promptly corrected. In addition to the NEC, other standards, such as those published by the National Fire Protection Association, or NFPA, may also provide guidance on the design, installation, and testing of emergency power systems. NFPA 101, the Life Safety Code, contains specific requirements for emergency lighting and power in various types of occupancies. These requirements are often more stringent than those in the NEC and should be carefully considered when designing an emergency power system. When working on emergency power systems, it is important to follow all applicable safety procedures. Electrical work can be hazardous, and it is essential to take precautions to prevent electric shock, arc flash, and other injuries. Always to energize the circuit before working on any electrical components. Use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and arc flash clothing. Follow lockout-tagout procedures to prevent accidental re-energization of the circuit. Be aware of the potential hazards of working with batteries, such as the risk of acid burns and explosions. Always wear appropriate PPE when handling batteries and follow the manufacturer's instructions for safe handling and disposal. Emergency power systems are a critical component of building safety. They provide a reliable source of power for essential systems during power outages and other emergencies, helping to protect lives and prevent injuries. By understanding the requirements of the NEC and other applicable codes and standards, and by following proper design, installation, and maintenance procedures, you can ensure that emergency power systems perform as expected when they are needed most. Generators used for emergency systems are often equipped with automatic transfer switches, or ATS. These switches automatically detect a loss of normal power and transfer the emergency load to the generator. The ATS is a critical component of the emergency power system and must be properly sized and configured to ensure reliable operation. The ATS should be tested regularly to verify that it is functioning correctly. The testing should include simulating a loss of normal power and verifying that the ATS transfers the load to the generator within the specified time. The ATS should also be inspected periodically to verify that all components are in good condition and that the switch is operating smoothly. Some emergency power systems are equipped with remote monitoring and control capabilities. These systems allow operators to monitor the status of the emergency power system from a remote location and to control certain functions, such as starting and stopping the generator. Remote monitoring and control can be a valuable tool for managing emergency power systems, particularly in large or complex facilities. However, it is important to ensure that the remote monitoring and control system is secure and that unauthorized access is prevented. The emergency power system should be designed to minimize the risk of downtime. This includes selecting reliable components, providing redundant systems, and implementing a robust maintenance program. The emergency power system should also be designed to be easily repaired and maintained. This includes providing adequate access to all components and ensuring that spare parts are readily available. The emergency power system should be designed to be energy efficient. This includes selecting energy-efficient components and implementing control strategies to minimize energy consumption. The emergency power system should also be designed to be environmentally friendly. This includes selecting components that are free of hazardous materials and implementing disposal procedures to minimize environmental impact. The NEC requires that emergency power systems be properly labeled. This includes labeling all components of the system, such as the generator ATS and battery backup system. The labeling should clearly identify the function of each component and should provide instructions for operation and maintenance. The labeling should be durable and should be resistant to environmental conditions. The emergency power system should be designed to be aesthetically pleasing. This includes selecting components that are visually appealing and arranging them in a neat and orderly manner. The emergency power system should also be designed to blend in with the surrounding environment. The emergency power system should be designed to be cost-effective. This includes selecting components that are competitively priced and implementing design strategies to minimize costs. The emergency power system should also be designed to be scalable. This includes selecting components that can be easily upgraded or expanded to meet future needs. The emergency power system should be designed to be flexible. This includes selecting components that can be easily reconfigured to meet changing requirements. The emergency power system should be designed to be reliable. This includes selecting components that have a proven track record of performance and implementing design strategies to minimize the risk of failure. The emergency power system should be designed to be maintainable. This includes selecting components that are easy to repair and maintain and implementing a robust maintenance program. The emergency power system should be designed to be safe. This includes selecting components that meet all applicable safety standards and implementing design strategies to minimize the risk of accidents. The emergency power system should be designed to be code compliant. This includes selecting components that meet all applicable codes and standards and implementing design strategies to ensure compliance.